So let's go for goodness of fit. And I think just because, no, this is a binomial. So there's my result up here at the top right. So here's the thing, is there are 100 squares. Each square, we've planted 5 flowers, and they either bloom or they don't with P. Suggest a suitable probability for the number of flowers found in each square. Well, a set number of flowers, so a set number of attempts. Each flower either blooms or doesn't, with a constant probability P of surviving. So if we say X is the number of flowers in each square, X is going to be a binomial 5P. Okay. Now, you would be forgiven for thinking, all right? You would be forgiven for thinking that you would be given P. You could be given P. But in this question, we haven't been given P, all right? So what's an appropriate value for P? What's an appropriate value for P? Well, what's the average proportion of flowers that have bloomed? All right. So what's the mean number? What's the mean number of flowers that have bloomed in each square? Well, in 3 squares, none of them bloomed. In 5 squares, 1 of them bloomed. In 28 squares, 2 of them bloomed. In 35 squares, 3 of them bloomed. In 20 squares, 4 of them bloomed. And in 9 squares, 5 of them bloomed. All right, that's the total number of flowers that have bloomed. How many flowers were there? Well, there were 5 flowers planted in each square, 100 squares. So let's find this out. All right. Or, as Brandon puts it, you can make the means match up. You can make the means match up. So you take the average number of flowers. So you could do that, or you could say the average number of, oh dear. You could say that the average number of flowers has to come out as NP, and we can go from there. So Snuffler, yeah, just E of X over N. What's that? 291 over 500, Cybers? I will trust you. So what's that? 0.582? Okay. So what's an appropriate value for C? Well, C will be, what is the probability then, using this, of getting 3 flowers blooming? We want the probability that X is equal to 3. And then we're going to scale that up. So that's the proportion of squares that will have 3 blooming flowers. Scale it up by 100. And I will show you how to use the calculator to get a lot of this out in a second. We want equals to, I'm being so lazy right now. This is outrageous. 0.582. So 34.44. Now, one thing I'll point out is in theory, the sum of these frequencies needs to come out as 100 because there are 100 squares. The sum of these frequencies should come out as 100. It might not for your expected frequencies. Why might it not come out as exactly 100? Well, because you've rounded, right? These numbers are all rounded. And if you happen to round them all up, what you hope to happen is some of them get rounded up, some of them get rounded down, and those roundings up and down cancel out. the exact values for these frequencies will add up to 100, but once you've rounded them, you might come out as 100.1, 100.2, or 99.9, right? Don't stress about that too much, right? That's accepted, that's internalized. Right, let's do our actual hypothesis test though. H0 binomial is a good fit. H1 binomial is not a good fit. Now, what we really want here is nu, which is our degrees of freedom. Now, how many degrees of freedom? Now, a degree of freedom is this. If I was going to come up with these numbers myself, if I was just going to make them up, how many of them can I choose? Well, you would think I could choose all 6 of them. You would think I can choose all 6 of them, but I can't. And the degrees of freedom isn't. So, few things to look at. Number 1, we're going to combine these 2 squares. We're going to combine these 2. Why? Because that frequency is less than 5. As part of this approximation up here that we're going to use, we need all our frequencies to be less than 5, at least 5. Okay, at least 5. So we're going to combine these. So we're going to combine these 2 to give us 9, 10.16, and we'll combine these to give us 8. So already we're down to 5, 1, 2, 3, 4, 5 degrees of freedom. But we lose a degree of freedom because the total has to come up to 100. So once I've picked 1, 2, 3, 4 of them, the 5th one is fixed in place because they need to add up to 100. So once I've picked 1, 2, 3, 4 of them, the 5th one is picked. And to be fair, we could have got this number just by doing 100 minus all of these other things, right? We could have just done 100 minus all of these things. So 5, because we want the frequencies to be at least 5, this expected frequency is far too small, so I'm going to combine these 2 boxes together. I'm going to combine these 2 boxes together, Luke. All right, because you need the expected frequencies to be at least 5. But we lose another degree of freedom. Why? Because the mean number of flowers in a square, right, we need that probability to match. Because I got the 0.582 from these numbers, these also have to come out with 0.582 as that same calculation. So because I used my data to approximate that P of 0.582, I have lost another degree of freedom. So the point is I can only pick 3 of these numbers. Once I've picked 3 of these numbers, the other 2 are locked in place. Why? One of them to make sure that the total is 100, the other one to make sure that we get a P of 0.582. So my degrees of freedom is 3. Now we can go to the calculator. You can do your test statistic up here by hand if you want to. However, we can go to statistics. We can clear our columns. And what we can do is, let's move that over to here. Let's move that over to here. So let's put our observed in the first column. So don't forget, we combine these 2. So 8, 28, 35, 29. We put in our expected frequencies, 10.16, 24.74, 34.44, 23.98, and 6.68. And then we can do a test. We can go test chi-squared. It is a goodness of fit test. Observed was list 1, expected was list 2. My degrees of freedom is 3. Bosh. It gives me my test statistic. So I get my chi-squared statistic is 2.364, and I get a p-value of 0.5. So actually this is very, very, very likely to get this level of p-value. Or if you want to, you can go get your critical value. You can go distribution, chi, inverse chi. You want, I think we want to go 0.95 because it's error to the left. Degrees of freedom is 3. And my critical value, oh no, maybe not. Yeah, my critical value would be 7.8. So it doesn't really matter how you go about this. You also get given a table with it all, right? You do get given a table with it all. Actually, I need this up so I can actually move this back to where it was. Yeah, Brandon, that's what we did. 5 minus 2 is 3, right? 5 minus 1 minus 1 is 3. Sorry, I hadn't seen that. Okay. We could also have gone, I think this will do chi-squared. Chi-squared. Tail, you always look at the right-hand tail for chi-squared. X is, well, what are we at? 2.364. Degrees of freedom, 3. Boop. And we can always move that to get 0.05. And there we go, 7.8147. So on the ClassWiz, I think you have to go full ham and calculate it yourself. Which is why quite often they just give you a couple of missing values, but you do need to do it yourself, unfortunately, and then go check the tables of values. Okay. So here, basically, what you're saying is, so chi-squared is a measure of how wrong your observed is versus the expected, right? Chi-squared is a measure of wrongness. So when would you break up with H0 if the wrongness is too high? So because that is less than 7.81 or that is bigger than 0.05, one of the two, insufficient evidence to reject H0. And then we're going to put in a conclusion, but we're going to move on. I'm having too much fun talking about stuff. So yeah, sorry, Anthony. It's on the ClassWiz, you're stuck doing it yourself as far as I'm aware, and then comparing to the tables.